Hello, my name is Rohan Dewan and I'm from Group 9 and today I'll be presenting the paper The Power of Two Choices in Randomized Load Balancing. Let me direct your attention to the top left square where I'll be discussing what are your real options for load balancing. So now let me paint the picture for you. You're in a grocery store, Black Friday, people everywhere. What do you do to choose the best line to pay and get out? So you could always just check all the lines, pick the shortest one, and get out. It's optimal. You'll find the best line, but it's extremely slow. And could you imagine doing that for thousands of servers or something like that if you're a job? That'd be very inefficient. The other option, you could put your trusty blindfold on, spin in a few circles, choose a line. That's efficient. But you and if say lots of people did this and that was the standard, many of you may be going to the same line. Not optimal. Option three, everyone does that. Everyone spins in circles, points at two different cues, trusty blindfold, and you choose the better of the two lines. And in this algorithm, we explore how this is actually nearly optimal. So two random choices can get you roughly global knowledge. So let me take you down to the bottom left. So D is actually the number of random servers to choose from. So what I'm really trying to show here is that for D equals 1, the expected wait time for each job is 1 over 1 minus lambda. So what is lambda? Lambda is the rate at which jobs arrive, and based on the rate they can be processed. And if as lambda approaches 1, the wait time, average time spent in the system approaches infinity. But if you notice for d equals 2, the actual rate at which it scales is logarithmically less, which is incredible. Now, also, what you want from a load balancing is you don't want like certain servers to have too long queue of jobs. So if I direct you to the top middle square, you will see that for d equals 1, the max queue length for this algorithm, according to the paper, is big O of log n, which is quite good. It's decently spread out, but it could still be quite a lot. But for d equals 2, when you have two choices, the maximum queue length is big O of log n, which is that really limits the amount of jobs that can be in each line. So let me take it down to the rate of decay for queue length. So just because you set an upper bound doesn't necessarily mean that it's well distributed. But the for d equals 1, the it's exponentially decaying for from 1 to 2, which is basically saying it decays pretty fast. But for d equals 2, that gets scaled up on a whole nother level. It get the odds of a server having more than two jobs waiting is much, much less than for d equals 1, which is incredible. And I'll direct you to the graph on the top right. So we ran our own simulation to see if there was any method to the madness. And for d equals 1, when you're given one random choice, um, you'll notice that the performance is exponentially slower, the wait time. The graph is the average time in the system over the arrival rate at the server, lambda. So you'll notice that for d equals 1, the time spent is much faster or much higher than for d equals 2 and 3, as d equals 2 and 3 is more optimal. So the key takeaways from all of this, that's what you guys really want to know. So that is that adding one more random choice and picking the shortest one leads to exponential improvement. Yes, as mentioned, as you can see from the graph, there's no global coordination needed, and the performance is close to optimal. And improvement for more than two of the two choices is just a linear scaling. Thank you.